So just, you don't need to do this, but square root of x kind of looks like this. It's going to be 416. And 0, 0. And so the problem is asking for the point C here, where the slope is of the tangent is going to be the same as this chord, I guess to call it. So first thing is, what is the slope? So delta y over delta x is what? 16 minus 0, 4 minus 0 is 4. That doesn't look right at all. That's because I can't do math. 4, 2 is the square root, not squared. So it's 1/2. So our function is square root of x. We want derivative of c to equal 1/2. That's the setup, and from there it should be pretty easy. Derivative of this, derivative of f of x, 1 over 2 square root of x. We want to set that equal to 1/2. So you can just look at that and see that x is going to equal 1. So if c equals 1, I guess that's 1, 1. Find c. Oh, we found c. C equals 1. Sometimes it helps to kind of, draw the graph to kind of see if this makes any sense at all. If maybe you can look and say, well, some other number like -3 or something. Well, no, this is a positive slope. All right, graph function secant line through endpoints. I guess I did that. And tangent line at C, f of c. That's this. And our tangent and secant line parallel, well, they have to. I made them that way. I gave them the same slope. The only thing I'm not clear, either the way the problem was written or the way it was transcribed, is did they want the equation of that tangent? Because that's just a matter of y minus 1 equals the slope 1/2. X minus 1, that's the point slope. That's the point slope version of the line. Is that okay?
Yeah.
Questions? Okay. All right, this is
Wait, one.
yes.
The question, so is the secant line always going to be the one that goes from 0 to 0 and then to the point about? Like, how would you find the secant line in the supplement?
Well, they have to give you 2 points.
Oh, so that is. So those 2 points are how you find the secant line then?
Yeah, see, this looks like an interval, right? It really, well, it is an interval, but the implication I take from the problem is that they want, the endpoints being the endpoints of that interval.
And the secant line is what, the line that connects between the.
Yeah, actually secant. Gosh, I forget whether, like if you have a circle, right, have a secant. Is the secant this line segment, or is it the line, I think it's the line segment. Yeah, but it's a technical issue that I will not be concerned about in this class. There's a bunch more homeworks now. Pass out again. There are some unnamed homeworks. If you think they might be yours, maybe check them out during the break. Credit. So, all right, so we're going to look at this next. This is a really, I don't know, I don't think you'll see a problem like this again until you have to take analysis. So to be clear, they're not even saying there's a solution. But is there one? Well, I mean, just as kind of a rationale test, here's kind of what x cubed looks like, and here's what using x looks like. So, you know, you add these two together, at some point they're going to go through zero. That satisfies me. They haven't asked for it. They haven't asked for you to show that it has a solution, just that it has at most one solution. So how do we go about that? This is just like a similar problem we did, I think with x cubed. And, oh, I know how you can show this it has a solution. You just pick something like, let's call this function x cubed plus e to the x. So we know that we can just say f of 1 is 1 plus e, and just pick something like f of negative 2, that's negative 8 plus e to the minus 2. So this is clearly greater than 0. This is less than 0. And we have the intermediate value theorem that tells us it has to go through 0 to get from positive to negative, because they're both, you know, this is continuous function. Okay, so we have, it has 1, and we want to show that it can only have 1. And this is in the section on the mean value theorem, so we're going to use the mean value theorem. Actually, I think we're going to use Rolle's theorem. So Rolle's theorem tells you you have some function that has 2 points, a and b, that are equal. Function has to be differentiable between these points and continuous on these points. And it says that there's going to be some point C where the derivative equals 0. So let's assume there are points A and B on this function that are equal. Since it has a solution, we can just assume that. Well, we're looking for solutions. So we'll just assume it has two solutions. They're both equal to 0. All right. So this, the derivative of this, must have some point C where the derivative is 0. So what's the derivative? It's 3x squared plus e to the x, and we want that equal to 0. And that's where we find our contradiction, because clearly 3x squared is, this has to be greater than or equal to 0, and e to the x has to be greater than or 0. So the left side is always greater than 0, it can never be 0. So again, this, they want you to formulate this in terms of a proof by contradiction. Your assumption is there are two solutions, here they are, A and B, and then we show that since the derivative can't be 0, which we know from the mean value theorem, we can conclude there's only one solution. This again is very much like a it's like a problem from a higher level math class where you have to do proofs. But since we showed you how to do it, threw one into the catch your question. People sneaking in, that's catching up. Yes?
I don't understand how we know that it's just one solution. Just because it can only be 0 once, or that it can't be 0, or?
Okay, I kind of ran over it, so let me see if I can describe the logic. Like the mean value of, assume two solutions. Right? Assume we have, this function has to go through the axis twice. Okay. So there have to be some A and B equal to 0. Well, this function is continuous everywhere. So we're satisfying 3 requirements of the mean value theorem. That it be, and it's differentiable everywhere. That it's continuous from here to here. It's differentiable, and yeah, that's what you need for the mean value theorem to kick in. And the mean value theorem says there is a point C where this is 0. The mean value theorem we take as, we proved it in class, but we take it as fundamental. So this tells us that there must be C where the derivative is 0. Now we look at the function, we find its derivative, and we see it can't be 0. So, if you want to be really open-minded, one of 2 things can be the case. Either the mean value theorem is wrong, or our assumption is wrong. Since we believe in the mean value theorem, right? Our assumption must be wrong. There can't be 2 solutions. It's kind of, a lot of math proofs are like this, by contradiction. It's kind of backwards. You assume something that you don't think is the case, and you see that it creates the consequences don't make any sense.
So because it can't be zero, it only has one solution?
Right, and we found that it has one solution. Right? Yeah, this is kind of the most sophisticated thinking you're going to see in this class. George?
I think I understand that now. Why? I think I understand that now. I don't know why. How you can tell just by looking at f of x equals x cubed plus e to the x. How you can tell that there is an f of a that equals f of b. Is that
You don't have to. I mean, that's the, okay. The way you can tell that there's an a equal to 0 is that there's some number greater than 0, there's some function value greater than 0, there's some function value less than 0. I don't need to know exactly what it is. So because it's continuous, it has to go through all the values, so it'll go through 0. So we know, this is okay. There is some solution. We assume there's two solutions, which is, kind of violating what we're trying to prove intentionally. We say, well, what if there are two solutions? Then there has to be some place where that function has a derivative of 0. But we can see immediately here that it can't.
so? That's also proving that there is no f of a equal to f of b as well.
That's a different question. We're showing there's no f of a equal f of b equals 0. I don't know if we've shown that, but that's easy to show too. The way you can show that is if you look at this, it's you can show it's a strictly increasing function, right? I could say more, but if it's strictly, the function only decreases, there can't be, it doesn't fail the horizontal test.
So yeah.
That also means it has an inverse, although I don't want to calculate the inverse. All right. Somebody came here. All right. Any other questions about this or the homework? Yes.
One more. This one is from the max and minimum one.
Okay. Fair game.
I think it's on the same page. I think it's still page 287.
Do you think if you,
I think it's still on page 287.
I don't have the book with me, but do you think you could try, or if you want to write it down, that would be easy. Yeah, I hate that question when people say, it's just, it's part of being a math teacher. Will it be on the exam? You won't see a question like this on the exam. If I could give you a take-home exam and give you 8 hours or a weekend to do it, and we were worried about learning to do proofs, then yeah. But seems like opportunity for a calculator to come in handy.
Do you want the,
What's the question?
partial work, which is 73.
73. This happens, this is not your fault. These are electrostatic. Try again. 74.
73.
73. Ooh, this is a great concern to young people. After an alcoholic beverage is consumed, the concentration of alcohol in the bloodstream, the blood alcohol concentration, or BAC, surges as the alcohol is absorbed, followed by a gradual decline as the alcohol is metabolized. This function models the average BAC measured in V per DL, gallons, grams per liter, of a group of 8 male students T hours after rapid consumption. Why would anyone rapidly consume alcohol? So it's sip it. Corresponding to one alcoholic drink. What is the maximum average BAC during the first 3 hours? When does it occur? The maximum average, oh, is that what this is? I mean, are they just asking for a maximum? And that's a T and that's an E. Yeah, I think that's it. They want to know what the max is. So what we want is C, T, well, 0.135. It's like a real world problem. Students are always asking for real world problems, so here it is. Assume T in hours. All right, well, we have to find the derivative of T, E to the whatnot. So we need to use, since this is a product, T times the derivative of E to the minus 2.08. That's E to the minus 2.802 times negative 2.802. Product rule plus E to the minus 2.802 T. T. And we want to know where that's 0. So, e to the minus 2082t, what does that look like? That's an exponentially decreasing. It's never 0. So we can divide it out. Well, we can divide this out too, right? So what are we left with? We're left with T times negative 2.802 plus 1 equals 0. Oh, that's a lot easier. T equals minus 1 over minus 2.802. 1 over 2.802. So that's what they're saying is that, you know, you drink some alcohol, it shoots up, reaches a peak, and then it drops off according to this equation. I think if you want to graph it, I think I got the right idea here. And so now they want to know, well, where is that peak? And we found it at 1 over 2.802, which you can divide that and come up with a figure. Other questions about that one?
How did you get to the smaller equation? I know that you got to do that one.
Okay, you can, this is all equal to 0, right? So I can divide by 0.135, and this goes away, right? Inside here, I've got this function e to the negative 2.802t, which I tried to point out is always positive. So we can divide by it. We can just divide it out, and we're left with this.
Divide it out, what do you mean, the law?
Okay. I skipped a step. 0.135 e minus 2.802t and negative 2.802t plus 1 equals 0. Is that okay? I'm factoring e to the negative 2.802t. It's over here now. Okay? This will never be equal to 0. It's a factor, but it'll never be equal to 0. So I can divide both sides of this equation by 0.135 e to the minus 2.802t. This cancels. This is 0. And you end up back where we were, which is negative 2.802t plus 1 equals 0. And then you solve for t. It seems like you're cheating, right? Because there's a t here you never have to deal with. But it doesn't, in this, it doesn't matter what t ends up being. It's still going to, both of these are going to be positive. It's going to cancel. All right. I'm going to pause again, see if there's any questions. All right, so I'm going to go over the exam. I apologize to any of you who did particularly well. In a couple of cases, at least a couple of cases, students didn't get things wrong, but I don't think this is going to take very long. I do think it's important given that we've had a lot of people had a lot of difficulty with the exam. So the limit x approaches 1, x cubed plus x squared minus x plus 1 equals what? This is a polynomial function. Polynomial functions are continuous everywhere, along with a lot of other functions we've talked about. So the limit as x approaches c of f of c for a continuous, the limit is x approaches c of f of x. Keeping in mind the limit and the value at the limit are not necessarily the same, but for a continuous function, they are the same. So this just becomes 1 plus 1 minus 1 plus 1 equals 2. All right, now, in contrast, this function is not continuous at 1, so we can't pull that trick. We can check. We can see that, well, this is 1 plus 1 minus 2 it goes to 0, and this goes to 0. If the top went to 0 and the bottom went to a constant, this would go to 0. If the numerator went to a constant and the denominator went to 0, this is going off to infinity. It's a infinite limit. But neither of these is the case. So for problems like this, we need to do something else. We're going to find this an even easier way to handle this probably on Thursday. But for now, your job was to factor this. This is x minus 1 times x plus 2, x minus 1. Is that right? Minus 2 plus 1, yeah. And then you use the fact that the limit of a product is the product of a limit. You didn't have to write all this out, you could just kind of see what was coming. And obvious, well, I don't know how obvious. The limit is x minus 1 over x minus 1. Well, it's 1 everywhere but at 1. So close to 1, it's 1. The limit here, well, again, we talked about this is a polynomial. So this is just 1 times 3 or 3. Yeah.
Are we also allowed to cross it out because you factor it, you can cross out x.
Yeah, you can skip a step and go, look.
Yeah, and then
These-
plug in x.
Yeah, now,
x is 1.
Again, we're dealing with a limit where the rules are a little funny. The rules are close to 1 is what we want, not at 1. I'm sorry, you were saying something.
Oh, I was just wondering if you could cross it out and then, because it says the limit is x approaches 1, you could put 1 in for x, you go x, so it would be 1 plus 2, and you get the same answer.
Yeah, yeah.
Can you do that?
Yeah, you're skipping a step, but I didn't tell you write down all the steps. If I said, I want a proof or something, or I want this very clear, I would care. But if you just kind of go, oh, I know, this is just 1, so it ends up, close to 1, it's 1, so it's 3. That would be perfectly adequate. Number 3, limit x approaches 9 of square root of x over x. Well, there's a couple ways you could think about this. The most simplistic way that this happens to work is I think I can plug in those numbers. Square root of root 9 is 3, over 9 is 1/3. You could think a little harder and you could say, this appears to be a continuous function, except it's 0, and we're not looking at 0. So it's continuous, so you can just plug in 9. The other way to look at it is, well, this is the limit as x approaches 9 of square root of x over the limit as x approaches 9 of x, which is equal to the square root of the limit as x approaches 9 of x over limit as x approaches 9 of x. This is your limit laws. And the limit as x approaches 9 of x is just 9, so it's the square root of 9, again, over 9 is 1/3. All right. Limit as x approaches 0, x cubed plus x squared. X squared. Well, again, we're going to pull the trick we did before. We're going to factor x squared times x plus 1 over x squared. These two go to 1, so this is just going to go to 1. Okay, so there was a hard limit problem. Number 5. Limit as x approaches 0. Square root of x plus 16 minus 4 over x.
The previous question was 2x squared. He's talking about wrong. It's x.
Did I copy it wrong?
Yeah.
Thank you. We did a problem exactly like this in class. There was a problem exactly like it on homework. So you just had to have paid attention and known that the way to solve this, well, if we look at it, denominator goes to 0, denominator goes to 0, so we don't know what the limit is easily. But if you multiply this by the square root of x plus 16 plus 4 over the square root of x plus 16 plus 4, which you can do because at 0, this is just 8 over 8, or 1. In the numerator, well, we have a minus b times a plus b. It's a squared minus b squared. So x plus 16 minus 16. And down below we have x over the square root of x plus 16 plus 4. And lo and behold, the 16's dropped. We have x over x. So at 0, we're just going to end up with 1 over square root of 16 plus 4, or 1/8. That was the hard limit problem. There's a limit at infinity problem. And we did some of these in class, and we're on homework. Limit x goes to infinity. And the way you handle this is you divide the top and the bottom by x squared. And you get 3 plus 2 over x plus 4 over. And it's deteriorating. 4 over x squared. 1 plus 1 over x squared. Again, the limit is x goes to infinity. We can use the limit clause to break this up. 2 over x as x goes to infinity, of course, goes to 0, as does 4 over x squared, as does 1 over x squared. This just becomes 3 over 1, 3. All right. That's the end of the limit questions. Are there any questions about those? I was somewhat encouraged by the fact that almost everyone did a number of the derivative problems correctly. 7 and 8 are about continuity. Mostly had to understand what continuity is. The first says, where is this function continuous? I interpreted someone telling me where it was not continuous as they understood it, even if they, under the heat of taking an exam, they didn't write it that way. So this is a rational function. Rational functions, they're continuous on their domain, but their domain does not include places where their denominator is 0. So the real question is, where is x squared plus 3x plus 2 equals 0? Well, we know how to do that. X plus 1 times x plus 2 equals 0. So this is continuous on the interval negative infinity to negative 1. Negative 1 to negative, I guess I have them backwards. Negative 2, negative 2, 1, and negative 1 to infinity. Now, you could write that all sorts of ways. You could say everywhere but negative 1 and negative 2. That would have been fine. Number 8, this is 7. I guess this was just, I have to rethink this. Did I trick somebody here? Thought this would be easy. Whereas this function, continuous, well, sine is continuous everywhere, cosine is continuous everywhere. We have a law of continuity, sum of two continuous functions is continuous. This is continuous everywhere. That seemed to be hard. I didn't intend it. The next problem is conceptually hard, but once, if you understand the concept, it's kind of ridiculously easy. So maybe the problem was I didn't get the concept down to you. Doesn't matter what the functions are. You have one function here, we'll call that f of x, and you have a function g, and you know that f of x is always greater than or equal to g of x on some interval. Right? Pick some interval from here to here. And you have some function, I guess I should have left some room here. You have some function h in between. So I have some function h that I know is dead. Is this dead? So that's g of that, h of x. And we have this thing called the Squeeze Theorem that applies to this. It says that if you have this condition on some interval, and the limit as x approaches some c of f of x is equal to the limit as x approaches the same c of g of x. In other words, h of x is squeezed between these. If these limits are equal at c, then the limit as x approaches c of h of x, well, it's the same thing. Let's call that L. So that's the concept. In this particular problem, we're interested in the limit as x approaches 1 of h of x. And f of x is a polynomial. G of x is a polynomial. F of 1 is -1 plus 2, 0. G of 1 is 1 plus 2 plus 3 is 5 minus 5 is 0. We've squeezed h. We don't know anything about h except it's continuous. It's always between these functions. So its limit has to be 0. So that was the Squeeze Theorem. That was the hard problem. All right. Any questions? Yes, George.
Phil, I feel compelled to ask that question. Where does that come up in real life, the Squeeze Theorem? Where would you ever use that?
Real life.
Yeah, real life.
Well, I'm trying to think. You're out on the oil field pumping oil. It shows up in math. There would be, typically you have some kind of limit you want to find. I don't know if this is going to be what I want it to be, but okay, look at that and go, well, it looks like it's going to 0, but sine is kind of going up and down. right? So you find two functions that this is between. Yeah, this is going to work. This is so both of these limits go to 0. Sine of x is always between, over x is always between these two. So we can find the limit. That's a simple example.
That's right.
Okay, it would be more fair to say somewhere in math, it's a real thing.
Right, not biology, like in population or anything like that.
Well, probably not, but again, you get this, there's this bridge, right? You need math, calculus to study biology. This is part of calculus. Maybe, you're right, maybe it doesn't show up in biology, or the result of it might, right? There might be some theorem that you use to get some formula, and to develop that theorem, maybe you need Squeeze Theorem. And now you know how many bacteria you're producing, or whatever flow of energy. All right. I'm probably going to disappoint myself. I'm hoping this won't take more than the first half of the comments, but that's all right. It's important. Okay, the next. If you miss any of these, you have to go back and you have to study and figure out why you missed them and make sure you can get problems like this. I'm just going to go through them as quickly as possible. These are just derivatives. Power rule, sum rule. Derivative is 2x plus 7. Power rule. F of x equals x to the 6th. Power rule, 6x to the 5th. It's just a formula. F of x equals square root of x, which is x to the 1/2. Power rule, so it's 1/2 x to the negative 1/2, or 1/2 square root of x, if you prefer. Now we get to a problem where you need to use the product rule. The derivative of the product is not the product of the derivatives. It's not. We have e to the x times x squared plus 2. These are the two items we're multiplying. Product rule says e to the x times the derivative of this plus this times e to the x. That's all you had to put. You wanted to factor the e to the x out, great. In some of your exams, you wrote down the wrong answer, but I looked backwards and you had the right answer at what I would have accepted, and then you did some algebra and got it wrong. And I just crossed it out and gave you credit, because we showed you knew how to do the calculus. Okay, 14 is the quotient rule. How many quotient rules did we do? I think we're going to hang on and get through the rest of this. Take a break. Derivative of x squared times x minus 1 minus derivative of x minus 1. That's 1 x squared over x minus 1 squared. It's the product rule. Now we get to, understandably, the hard derivative problems because they use the chain rule. The chain rule is hard because you have to kind of, in your head, or if you want to write it down, you have to kind of separate things out. Now, by the end of this class, you should be able to just look at this and write down the answer. But let's treat this as f of x equals g of h of x. Where g of x is square root of x and h of x is x squared plus 3x plus 1. Let's find these derivatives real quickly. G prime, again, we know is 1 over 2 square root of x. Derivative of h of x is, again, just power rule 2x plus 3. So our derivative of f of x is the derivative of g of h of x, which is derivative of g at h times h prime derivative of h. So what's that? Well, g prime is 1 over 2 square root of x. 1 over 2 square root of x, but at h of x, which is x cubed, x squared, plus 3x plus 1, times derivative of h of x, 2x plus 3. Now, you can skip all this stuff. You can just look at that and go, something under the square root sign. So it's going to be 1 over 2 over that thing under the square root sign. But now we have to multiply by the derivative of this. I hope by the end of this class you can just do that in your head or with paper. No, wait. This is also chain rule. Find the derivative of the sine of x squared. There was some confusion some students had with the meaning of this because they got all sorts of answers. I guess a lot of it was confusion with the chain rule. So the derivative of the sine of something is the cosine of that something times the derivative of that something. That's all there is. 1, 2, 3, 4, 5, 6. At least 6 interestingly unique answers that all showed some piece missing. All right. I'm gonna give number 17 short shrift here. I gave you a polynomial function, and I asked for the equation of a line that went through a point. There's a tangent that goes through that point. So, I think so you find the derivative, right, to find the slope. And you find the slope at that point, which is 1, so it's did I write something wrong? Oh, 9 minus 4 plus 5 is 10. So that's the slope And then I think some people had trouble with writing the equation of a line. In your Algebra 2 class, you might get a problem. M equals 10, and it goes to point 1, 3. What's the equation? You know the point slope form, it's just that, right? 1 goes here, 3 goes here, 10 goes here. If you're having trouble at that level, I have my sympathy, but you're really going to have to work hard for the rest of this class, because that shows there's some basic skills missing that I don't know what we could do anything about. All right, hard problem. Find y dx at the point -1, 3. We have to do implicit differentiation, probably the hardest thing we did in this class, hardest thing to understand. We treat y as a function of x. So when we find its derivative, we need to use the chain rule. We find the derivative 3x squared minus, here we have a product rule, x times the derivative of y plus y times the derivative of x plus the derivative of y equals 0. Plug in -3, 1 for x and y and solve for y prime, and you get 0. 19 is, again, yes, conceptually you had to kind of understand what I was getting at, but from there it was pretty simple. I write down the definition of the derivative of the sine of x. I hope no one got confused and thought I expected you to go through all that work in the book and derive, expand this and find, prove that what happens to sine of x or sine of h over h. Just what's the derivative of the sine of x? It's the cosine of x. That's all there was to it. And finally, number 20, I made a mistake. It was completely in your favor. Stop. Completely in your favor. I forgot to write down that I wanted the future value given continuous compounding. It's like present value is $1,000. Interest is 4%, 100. T is in years, whatever. It's 4% per year. So I didn't even say compounded interest. So someone wrote $1,000 times 1 plus RT. Well, that was true. Some people thought a little further ahead and said, all right, 1 plus R over N, NT. I compliment you on understanding, if you break it up into N periods, you get that. But if you do it continuously, it just becomes e to the RT, and that's all I was asking. A strangely difficult problem for some reason. All right, any questions about the exams? I think everybody knows you can correct your exam, you can get some more credit after I really want you to learn this. You know, don't fudge with this. Don't, you know, make sure you understand how to do these problems. If you don't, I could give you full credit, but you're not gonna do very well in this class going forward. If you need assistance, come to office hours or come to the math tutoring. Please, don't take this as seriously as you can. And for the students who aren't here, if you know any of them, please pass this on to them. I'm sure they need, some of them need assistance too. All right, I'm going to take a break. I'll be back in a few minutes and we'll look at a math subject. So now we're going to look section 4.3, which is just going to say the shape of graphs. We all have Desmos at our control. We all can get a TI. So you can just plug in a function and look at its graph. 30 years ago, this is probably the same chapter as in Stewart, but we actually want people to draw graphs. I'm not that interested in it. What I'm interested in is what are the things we learn from calculus without a graph. We have some function to talk about. There are things that you should have come to this class with from your pre-calculus days, but I just think I'll go over them real quickly. If we set the function equal to 0 and we solve for x, we might find no solutions, 1, many solutions. And for some function, those points would represent where the function goes through the x-axis, the solutions or the roots. So we can always try and solve for, the function for 0 and find out where those solutions are. We have some kind of rational function. It looks like this, let's say. You know that at some point the denominator is going to be 0, and that's at -1 here. 1 over 0, well, that's undefined, but as you get close to it, it's going to blow up. And you're going to get a vertical asymptote. Should be aware of that. In the case of other rational functions that you have to look at carefully, you might have something like 3x squared or 2x squared plus x plus 3. And if you look at the end behavior of this function, right? Well, it could do all sorts of things near 0. It could wiggle around, but at some point, it's gonna head for 3/2, and there'll be a horizontal asymptote. So you should be aware of that. If you don't have this situation, right, where the degrees are the same, well, if you have a higher degree in the denominator, it's going to act like a polynomial when you get far away from 0. So if we just make this x cubed, we know that somewhere out here it's going to go off. And since it's odd, down here it's going to go down. If this was an even number, they both go up, or they both go down if the coefficient is negative. So this is all stuff you should have known before you got here. And some of it may come up in this chapter. Let's talk for a minute about what calculus would tell us. We have this idea of a derivative, which is a function that tells us the slope of the tangent at that point. And if the derivative is greater than 0 on some interval, indicate that, what does that tell us? It's a positive slope on that interval. That tells us the function is increasing in that interval. If it's less than 0 on some interval, it's decreasing. Well, we're not that interested in it being 0 on an interval. That would be just a horizontal line. The book calls this the increasing decreasing test. So let's take a look at some example of what that might, how that might work for some function. So I'm going to pick a suspiciously manipulative function here. So polynomial 3x to the 4th minus 4x cubed minus 12x squared plus 5. And we find its derivative. So we get 12x cubed minus 12x squared minus 24x, which has a factor of 12x. It's 2. And that's 12x times x minus 1 times x plus 1. Okay, that's the derivative. So we want to know, where is the derivative positive and negative? Well, if we start off, well, we can see there's three important points here, where the derivative is 0. So it's 0, 1, negative 1. And, this is a polynomial, it's smooth. And so these represent the only places where the sign of the derivative can change. So let's take a look on either side of it. If we said negative 2, we get 24 times negative 2. So b times negative 3 times negative 1. So we've got 3 negatives, it's negative. So down here, the derivative is negative, and that tells us that the function is decreasing. Well, as you go, to the left, this function gets larger and larger. So as it comes back in, you'd expect, this is the derivative I'm looking at. You'd expect the function to kind of come down from the heavens. We didn't solve for where this crosses 0. That would be a little challenging at this point. All right, so we know it's decreasing here on this interval. What about here between -1 and 1? Well, we can try -1. Negative a half, so 12 times negative a half. Negative a half minus 1 is what? You don't care, it's a negative number. This is a positive number. So 2 negatives is a positive. So we know that between these two intervals, on this interval, it's increasing. So, where it goes through the x-axis, I don't know. But at this point, it's going to start going up again. Now we want to look at over here at 1/2. Well, very quickly, positive, positive, negative. So at 1, it's going to start decreasing again. And then we can ask, well, what happens way out here? Well, we can just pick 2, and it's all positive. So how does that happen? I guess at 1, it's going to start moving off. I don't really know much about this, but I do know from here to here it's decreasing, increasing. I'm sorry. Did I get that wrong?
In your roots, it's x minus q.
Plus, minus, it's decreasing. So it's increasing to here and then decreasing. I'm sorry, what you were saying?
Oh, in your roots, so instead of x minus 1, x plus 1, it's x minus 2.
All right, say it one more time slowly. I'm with you. You're
So,
saying, what am I plugging in?
not plugging in, but we're going after the x squared minus x minus 2.
Oh, did I make a
It's
mistake?
at the very bottom on the x minus 2 instead of x minus 1.
The fourth line now.
One more.
Here?
Straight down where it says x minus 1, x plus 1.
Yeah.
X minus-
Oh,
The other way.
thank you.
It's x plus 1.
It's minus 2 plus 1. Okay. So we have to move, okay, so this is now 2, and this is -2. No, this is 2, and this is -1. Thank you. Yeah. Oh. Small errors will expand. Okay, so this is an important test you can use on any function where its derivative is greater than 0, it's increasing, where its derivative is less than 0, it's decreasing. Excuse me. Now, of course, where the derivative is 0, a function might be changing direction, in which case you might get a maximum or a minimum. We looked at that in the last chapter. You also could have a function like f of x equals absolute value of x. You have a critical point, and the derivative changes here from negative to positive, so you can have a minimum there. So where the derivative changes from positive to negative or negative to positive, you can have a maximum or minimum. This is called the first derivative test. It's equally possible that at some point the derivative is 0, but on one side of the point it's positive, on the other it's positive. And here you get kind of a saddle point here. We'll talk about that in a minute. So it's not always the case that this means that you have a maximum or a minimum. So one thing you can do, at least for a continuous function, is you can look at the second derivative. That's going to tell you what the first derivative is doing. If the second derivative is greater than 0, at that point, what does that tell you? Well, if you have maximum, your derivative is decreasing. I'm sorry. This would be a maximum. This is the second derivative test. If the second derivative is greater than 0, right? And in this condition, it's increasing, right? It's going from negative to positive. Then you have a minimum. And to me, this is a really good thing to get a feel for. What happens when it's 0? That's this condition. It goes from increasing to 0, right? And then it can increase again. What happens to the second derivative here? All right, what is this? What's the phenomenon here? And I want you to look. Use another pen here. If you look here, look at this curve. It kind of has a central point here. It's like I don't want to say it's a circle, but it curves downward. Whereas over here, it's curving upwards. And this point here, where the second derivative is 0, reflects the point where that changes. And that's called a point of inflection. Now, you're artistically inclined, and you're drawing freehand curve. If you look along here, there's some point where it switches, right? And you want to get a feel for what that means. Right? Up to here, it's curved downward. From here on, it's curved upward. Sometimes that can be quite subtle. If you're looking at a graph, you might see a point like this. You might say to yourself, well, I can see it's curved down over here and it's curved up over here. Where does that change happen? Somewhere in here. And algebraically, you can, if you have a function, you can solve for the second derivative and somewhere at 0 and find those points. So that's what the second derivative function tells us. It tells us where these points of inflection exist. I think we have time to do could do one example. Again, what I want to make clear is, I mean, the homework in the book is going to say things like, here's a function, find these points, draw the graph. I'm not that concerned about you being able to draw the graph because, again, we have computer graphic systems. You can just plug in a function and draw the graph. I just want you to be aware of how these different properties, first derivative test, increasing, decreasing test, how they apply to the graph you're looking at. So, with that in mind, let's look at the function f of x equals x plus 2 sine of x. And without going through all the work, let's take a look at what it's going to look like initially. And it's going to do something like this over here. So let's see how this whole stuff applies. So the first thing we want to do is find the derivative. So the derivative is 1 plus 2 cosine of x. And we want to ask, okay, let's find out where that's 0. So that would be where cosine of x is equal to negative 1/2. Draw our unit circle. Our cosine is the y coordinate, right? The x coordinate. So what's this angle here? This is a 60-degree angle, so 120, what's 120? 2 pi over 3. But also here. So what's that angle? That's pi plus 60 degrees. That's 4 pi over 3. But again, you have a cosine here, so every 2 pi, this is going to repeat. So we write it this way, plus 2 pi n. All right, so now let's look at our graph. And we can kind of see immediately. 2 pi is going to represent a maximum here. And 4 pi is going to represent a minimum. And then the function is going to increase and it's going to repeat. So that kind of gives us a sense of where these maximums and minimums are, the fact that they're going to repeat because we have a periodic function here. What about the points of inflection? Somewhere in here, this is going to change from curving downward to curving upward. And then again here, it's going to do the same thing, and it's going to repeat that. So to find that, we would use the second derivative. Derivative of the derivative, right? It's going to be equal to negative 2 sine of x. And we want to know where that's 0. Well, where's the sine of x 0? I'll draw a diagram here. 0. Certainly going to be 0. Over here at pi, it's going to be 0. And then it's going to repeat. Plus 2 pi, plus 2 pi. I didn't draw any further, but in fact, if I did, you'd see that at exactly 0, it's going to change from curving downward to curving upward as we go to the left. And here we have at pi again, 0 pi. Here again, it's going to change its curvature. So you want to look at that, kind of get a feel for that. I think that's probably enough for today. We're going to do a little more with this on Thursday before moving on. Again, I'll post the homework, but don't feel like you need to start it yet. It will not due till next week. If you want to start taking a look at some of the problems, maybe about some questions for Thursday. I think that's it. I will be in office hours today, of course. For Thursday, there's a little change in that we're going to try between 12 and 12:30. The overheating one with the other professors. But, I'll do my, if you want office hours on Thursday, let me know, and I can be there after that.